because I think I can make it more rich. But I made up a new data set. The data values in this data set span from 0 up to 20. Now I've got them hidden somewhere behind the graph, and what I've done with this Monte Carlo simulation, you're going to learn a lot about these in this class. It's ways of using computer technology to simulate your guys' experiences, like the key experiment. I got data from you guys. I also got data from the class on Monday, Wednesday. I also got data from my last term's classes on Tuesday, Thursday, and Monday, Wednesday. I've been collecting that data for a long, long time. Very long time. You'll see the results in a minute. What this allows me to do is look at 1,000 randomly selected points. If I press F9, I get 1,000 different ones. If I press F9, I get 1,000 different ones. There's a random number generator. Basically, you guys are like a random number generator based on how many keys you have in your pocket, right? I don't know how many keys you have in your pocket. I know you have at least 0, and you probably have at most 30. Probably 20 realistically. So somewhere between that number is the number of keys you guys draw on a usual basis. So what I'm doing is I'm making you guys be a 1 or a 0 inside of a little tiny computerized circuit right now. And when I press F9, it's like spinning a roulette wheel to decide how many keys you have. So what I'm doing is I'm simulating thousands of students and then collecting the data here. David, go.
Why is it that the 3 times we saw the randomly selected data points, there's always 9 through 11 being the most selected?
Hold that thought, if you don't mind. It's hidden.
I sure will.
Well, then don't wait. We'll do it right now. See, it says normal right now.
I'll hold it.
No. Let's actually do it right now. You see how it says normal right there on that tab? This is where I ran out of time. There's data called normally distributed data. There's data called Poisson distributed data. There's data called binomially distributed data. There's data called, what's that one that's shaped like this? It's one shaped like a U. I forget what it's called right now. Different types of data behave differently. The U-shaped one, for example, is a good way of modeling failure of machinery. How many of you guys have bought something in a store, a machine that broke right away and to send it back? Has that happened to you in your lifetime? I'm sure it has, right? It doesn't happen very often, but it's more likely that it's going to break right away. Well, the joke is it breaks 3 days after the warranty wears up. But, you know, and if the manufacturers know how long that is, they can actually be criminal about it. But regardless, the curve of failure is shaped like a U. There's an infant mortality failure, and then there's a period of time where the thing works just fine, and then it wears out and begins to fail again. So there's all these different shapes of data, Dave. I just stuck with the normal distribution for the first one. So the reason why you're seeing the hump in the middle is because that's where most of the data is for the normal. It's not just randomly picking from a uniform distribution, it's picking from a special kind of distribution. Okay. This course, by the time we're done, we'll have explored at least 2, if not 3 or 4 of them. So this is just one of many I'll build eventually. So the idea is it is fluctuating within that shape. Just so you know, I'll go back to the PowerPoint for a second. So this was your guys' keys right here, right? This is what historically it's been over about 1,000 different students. You look almost identical to them, don't you? On a micro scale, you look like a fractal of the overall. So what I'm doing is I'm pulling a distribution that I know exists and just sampling from that. Great question, great question. All right, back to the Excel. So the front histogram, the blue one, in the blue one, was it somebody in this class that said, why don't we just make the histograms be 1 wide? Was that somebody in here? I thought it was. When we make histograms, why make them go like 0 to 2, and 3 to 5, and 6 to 8? Why don't you make them go 0, 1, 2, 3? Did somebody ask that in here? I love that question. I'm going to give you credit for it. So I do like that too, and that's what I did in the blue one. Right now, there are no 0s, there's 1, 1, no 2s. There are 3 3s, 5 4s, 35 5s. If I press F9 again, it changed slightly, didn't it? I got no 0s, no 1s, no 2s, a 3, 8 4s, 22 5s. And it's going to keep changing every time and it's going to keep track, the blue keeps track. Over here, the raw data average is going to be at 10. It has to be at 10 because of that distribution. Give me 8 weeks and we'll develop that idea. Promise. Promise, and we'll let you hang on that one. That's going to stay at 10. But that's if you actually have all the individual raw data points, right? If you actually exactly have all the raw data points. What if you don't? Well, you very often don't, right, Chrissy? Chrissy, thank you. You very often don't. You very often are given, say, this histogram in the back, which has them grouped together. So look at this one. See how it says 3, the red one back here? There are 0, 0s, 0, 1, and 3 2s. That means altogether there are 3 things in that bar from 0 to 2. Here, there are 5 3s, 11 4s, and 28 5s. Altogether, that's 42 things in that bar from 3 to 5. Same thing as your key document, right? Even the same spacing as your key document. Fair so far? We good? We're fair-ish. Now notice, we're going to assume everybody in 0 through 2 is a 1. We're going to assume everybody from 5 to 26 is a 4. Well, you can see there's a problem already, isn't there? Because when you look at, say, 3 through 5, you're assuming they're all 4s. There's a buttload more 5s than 4s. So by calling them 4s, you're actually underestimating what's in there, aren't you? Right. Does that make sense? Because you're picking the middle value, but the most common value is actually 5. Huh. And then we do it again right here. Right, 6 through 8, we're going to assume they're all 7s. But there's actually more 8s. Crap. But notice this. When I average the red distribution, watch that number. What do you notice about the average of the group distribution compared to the true 10? What do you notice? I'm going to go ahead and hold it down. It's kind of fun to watch it dance. 9, 10, 9.8, 9.9, 10.1, 10.2, 9.9, 10.2, 10.3. David, what were you going to say? Go ahead, you were going to say something.
So it's close, within like 0.2, 0.3.
It really is. I mean, right now it's within 0.03. That's pretty damn good. Let's let it go again. Okay, not bad, right?
Right.
0.05. A little bit over, 0.04 over. It's really damn close, right? But wait a minute, how could it be over? We're so underestimated over here. These should be way under, right? Wait a minute, is it? I want to say Lucas, that's not right.
Nope, Aaron.
Aaron! 5 letters, I guessed.
As it goes around the other side, it averages out. So
The trick, thank you, Aaron. Yes, when you go around to the other side, we were underestimating here. We're going to be overestimating over here, and it's a wash. It washes out. The over and the underestimates wash out on average over time. Now, I'm not going to tell you that there won't be some period of time when I'm sitting in this class and I press F9 and this graph doesn't do something weird like this. It can happen. Chances are if it happens, none of us will even notice it. Because it'll go by so quickly, you'll be like, I think something just happened, but I could have been blinking. It can happen, but it doesn't happen on average. It doesn't happen with any kind of proportional behavior. David, go.
Plus, like even like with the 6 to 8 column, if you average all 3 of those out, it's going to come with a number that's closer to 7 than it is to the other 2.
Absolutely, friend. Now, the reason I don't like, this is not a complete demonstration yet. I need more distributions. I like your guys' distribution because it's not bell-shaped. Your distribution is cool. It's got that cool tail on the end. Let me go back to yours. If we go back to this one, this is the historical data right here. I love this. This guy over here, 29 keys that one day. I mean, it was awesome. It was totally awesome. I heard it hit the desk. That's not a bell curve. This is a leaning bell curve. It's like the bell curve was here, and then it got shoved this way. So in order to do it that way, I've got to apply the same Monte Carlo approach to non-symmetric curves, which we can do. I just ran out of time to do it. I mean, I got to do things like sleep and go to soccer practice. So we'll get around to that, but the same logic occurs. It's called the law of large numbers. Things equalize. Things equalize. And that's why the averages are okay to group. It's totally fine. It works every time. Pretty badass, huh? Maybe. You don't think it's as badass as I do. That's okay. Just realize it is badass. Because as Christy said, in the lieu of raw data, we can still get a meaningful answer. Fair? Before we leave this idea of grouped averages, I want to do one more example. We might start it before break and then move to after break. We got a little bit of a late start because of Brandy. Totally worth it. There's one weighted, these are called weighted averages. When you do these, whenever you have data given to you like this, and you make that assumption about the center of each data set, 1, 4, 7, 10, whenever you find a median or a mode or an average based off of that, you got a little bit of inaccuracy, you got to call it a weighted average. Okay, and you've used these for years. Like, can anybody think of one very particular important weighted average that you guys have dealt with in your lives? As, I don't know, students?
Grades.
Oh, yeah.
GPA. A GPA is a perfect example of a weighted average. Anybody ever think of it that way? I'm sorry, I didn't mean to say something that just...
No.
No. Is it okay to talk about it?
Oh, it's fine.
Okay, the way your face fell. Okay, all right.